session this morning. James Ball is a physics teacher with the Upper Grand District School Board. He loves physics, although not as much as his family, but pretty close. When he isn't teaching physics, he's probably traveling, officiating a swim meet, or paddling a canoe. He's been teaching science for 29 years. His classroom today looks nothing like what it did when he started teaching. The students are engaged in peer instruction. James' lessons are designed to ensure that the students are active learners. His varied teaching styles are based on physics education research and are designed to improve both student understanding and engagement. Some of you may know that James is a very active member of the Ontario Association of Physics Teachers and a long-time member of their executive. And he was the recipient last year of the Erwin Lesnick Award of State. So please welcome James Ball.
Thank you very much, Ralph. I had the pleasure actually being involved in hosting our conference at Guelph 2 years ago, and it was a great pleasure that Ralph could come and give us a presentation. So I appreciate you being here, and thank you. I'm going to try and avoid using the mic. Let me know if you can't hear me. Peer instruction means you need peers. So if you're at a table of one, I'm going to ask you to move. If you're at a table of two, I'm actually going to ask you to move. Group or peer instruction works best if you've got at least three involved in the discussion. So if you could just take a minute to move, and if you haven't done so, take a moment to introduce yourself around the table, because you're going to be working together.
Before we get to the actual presentation, I wanted to talk to you a little bit about my classroom and how I make it framed such that peer instruction is
So peer instruction works. And so what happens is, the very first day my students arrive, there's a name card on their desk. And I did not make name cards for you. But every one of my classes, they arrive, there's name cards there. And that's not to help me learn their names. It's actually completely counterproductive, because the next day when they come in, they're in a geographically different place. So you can't do, oh, okay, that is such and such, and look at your seating plan. There is no seating plan. So it makes it worse for learning names. But what it means is that new student who's just arrived from Syria doesn't have to think about, where am I going to sit? Who am I going to sit with? They walk in, they know. They just walk in, find the name, and they sit down. And they're working with people that are around them. And then the next day they come in, and they're sitting, I put the cards out randomly, so they're sitting with different people, and those, again, they're going to work together with those people. And I do that for 2 weeks, so that they've worked with every single person in the classroom. And the idea is that the class succeeds when everyone interacts. And I tell them right off the beginning, you're going to learn way more from each other than from me. Right? And that will be true today. The discussion, the interaction happens is much more effective than listening to me. And I apologize, I'm going to be talking more than I ever like to talk, because if I'm talking, they're usually not learning. So I will have to do a little bit of that today. I also want to explain the technology that we're using. So this is the technology that we're using today. These are clickers. Well, not really. We do a lot of conceptual-based problems. So multiple choice questions that are not about using a calculator, not about using an equation. They're about fundamental understanding. And it's been shown that if their conceptual understanding is deep, that they're more successful. So day one, I give these out to them, and then I say, all right, what's going to happen is I'm going to put up a question. Every one of those answers are good. They have meaning. They're valid. There will be a best answer, but all of the answers should tell you something or may actually lead to an uncovering of a misconception. So all of them are valid. So there's no silly answers or no misleading answers. They're all valid. And then I say to them, it's okay to pick the best one. In fact, I would argue that's the best way to have real learning happen in the classroom. So what I do is put up a question and say, okay, there's no discussion at this point. I'm going to give you a minute or 2 minutes, it depends on the question, to try and come up with the best answer. And then I'm going to ask you to hold up the answers. Don't look around and see what everyone else is doing. There's no learning that happened. In fact, a couple of days ago I did it with my class, and I could see some of them looking around and changing their answer. And I had to remind them that we all missed an opportunity for learning there. Both the groups that had the best answer and the groups that perhaps didn't. That discussion, there wasn't any reason for a discussion. So they hold them up. What invariably happens is all of the answers are out there. If it's a well-designed question, you'll see all of the answers. And then I say, okay, go and find someone with a different answer and discuss. Try and convince them as to why you think yours is the best. And it's good because they actually physically get up and move around. And that's crucial. Sitting for 75 minutes is not good. And then after that discussion, I ask them to hold up their answers again. And what usually happens is they start to move towards two answers. In the end, it's A's go convince B's, B's convince A's, and 9 times out of 10, they will come to the best solution. The ones who understood it understand it better because they had to discuss it, they had to convince their peers. And the ones who had a misconception or picked perhaps not the best answer saw the merits in their answer, but also realized there was a better choice. All right, so that's my classroom, and it involves a lot of peer instruction. Normally I'd have whiteboards, but I'm glad I didn't try and bring whiteboards today. I clearly would not have had enough. So anyway, that was sort of semi-serious. Most of the rest of this is going to be anything but serious. I mean, it's all about 1950s cartoons. All right. So a lot of you are significantly younger than me. I remember Saturday mornings, late 60s, early 70s. Cartoons came on only Saturday mornings. I had to do a little history lesson with my students. Right? The TV actually only turned on at 7. There was nothing. There was just a screen image. And so Saturday morning were cartoons, and Bugs Bunny and Roadrunner were on at 8. I do have to apologize for any biologists. This is it. This is all you get. Binomial nomenclature. It always starts that way. He never does well. So just these cartoons started in the 50s. The entire premise, and it went on for I don't know how many years, is really simple. It's a coyote with an infinite budget. He's always buying all of the latest equipment from Acme Corporation. And the attempt is to try and capture the Roadrunner. Why he didn't go to the grocery store with that budget, I don't know. And to do so, he has elaborate plans. Really, really elaborate plans. And it never, ever works. So, because not all of you have seen it, I thought I'd give you a little taste. They were all 5-minute little movies. So here's a taste. It's always a play on words. Really quite strong. All right. So my interest in this actually stems back to a lecture I went to during an undergrad, while I was doing my undergrad, entitled "The Wile E. Coyote Impossibility." And I've been using it with my grade 11s for basically 30 years. And then with the internet and YouTube, I now suddenly had all of these cartoons available, or at least ones that are more than 50 years old. I think that's when the copyright issue comes into play. So the first 20 episodes are all up there. So what do we do with it? So sometimes he actually gets it right. Sometimes it gets really nicely at our misconceptions. Sometimes it's just so frighteningly wrong that you can actually use it to both entertain and to instruct. And sometimes it's all of them. All right. So this is one I showed my students a couple of weeks ago. It's just a little clip. So for those of you who aren't physics teachers, Newton's first law basically says things want to keep on doing what they're already doing. i.e. they're lazy. So they either want to sit there and do nothing, or they want to continue doing what they're already doing, so continue moving. So we're going to look at this, and then you're going to discuss at your table how this video demonstrates it. Okay, discuss. It's not sophisticated at any level. Yeah, well, the humor is total. But I think it's No. Okay, can I ask anyone who would like to share? How does it demonstrate things you want to keep on doing what you're already doing? It does so in a number of different ways. Give me one. I heard the discussion. I know you got it. Yes, thank you.
So when the rocket,
Yep.
when he was following the Roadrunner could go up a little hill, but the rocket can't just come straight and whatever. So it wants to go straight like it's doing, so when it's got kind of
Nice. Excellent.
I just wasn't sure whether I saw it correctly, but it seemed like the height of the wall was sort of about, a little bit above the coyote, so he had to go a little bit up. He didn't go straight. I don't know. Maybe I was like, I'm not sure if I saw it. I'm not sure. You should have been on this way.
Are you? I'm just perhaps not very sure.
Okay, so it's the thing. He goes up and around. Oh, he not. Oh, he doesn't. Oh, it's just. Okay, so.
It's close. It's
That was
close.
the foam or whatever it is, the gas that goes, that went around, that, not the coyote. Okay, good.
All right. Anything else?
False.
Sure.
He seemed to catch up to the Roadrunner after that point in time, almost like he had been accelerated.
Nice.
Or the Roadrunner decelerated.
Yeah, leave it on the assumption as well.
Okay, he was teasing. The Roadrunner was teasing him.
Which he does.
Okay.
Yes.
Anything else? There's kind of a slightly disturbing one at the end, which my students seem to quite like.
notice his back end keeps on doing what it was already doing, meeting his front end. And he always seems to recover, so. Okay, so we did that. There's another one. Discuss. All right, let's hear some thoughts. Give me some ideas. What do you think? What's right? What's wrong? Does it in fact demonstrate the interest first? Yes.
So, coyote's object at rest will stay at rest.
Sure. Excellent. And it very nicely demonstrates that. Anything problematic about it?
The rocket just hanging
I-
there. Started.
It's on a stick, but it's
That's more realistic.
it's like one of those Roman candles.
There you go.
Bottle rockets. So it's a fairly large bottle rocket. Yes.
That it's exaggerated delay of the coyote won't fall the right way, but there's for comic effect that he has a chance to make an expression and say, oops, and then
I think that's one of the first laws of cartoon physics, is you only fall when you're aware. Oh, I'm sure there has been, yes. And the other thing I would argue is that if there's enough friction to remove most of his fur, it probably was applying enough of a force on him to kind of move him forward. But the key idea, all right, this is you're introducing this to your students who haven't heard it before. One more. Okay, so there's multiple examples there. Discuss. What's right, what's wrong?
have to say? What do you get out of that? Yes.
We're gonna call it select or
Okay, I like that. Can you?
The objects are saying, so the propeller goes to this lane state, and goes like that.
Nice. And always to ensure the end result, which is said grenade blowing up next to said coyote. All right. So, Newton's third law, which is actually probably the most abstract and the most difficult for our students to understand, says that in our universe, all forces come in pairs. When I push on you, you push immediately back on me with exactly the same force. Sometimes it's obvious, other times it's less obvious. Right? I'm using Newton's third law right now to move around the room because I'm pushing the Earth backwards and the Earth is pushing me forwards. So they call them action-reaction pairs. I'm not keen on that because it implies one happens before the other. But here's a nice example of, well, let's just write them wrong. Okay, so I want you to discuss both what's wrong. Clearly there's some very wrong things, but there are actually some elements that are correct and worth discussing with students. So discuss, please. I'm going to add one more dimension to the discussion. Why is this either funny or intended to be funny? So why would our students either think this is funny, or why were the writers expecting people to find it funny? So just add that to the discussion. Because it really gets at the physics. profound and very important.
Yeah, we're just discussing, students know physics. They already know it. They don't understand the steps and the processes and how to break it down. But students innately have knowledge of physics every time they do one. They are scanning the surroundings. They're calculating car speed. They're calculating distance. They're calculating probability of collision. They have a knowledge of physics. They just don't know they know it.
And I would argue that's at the heart of why that's funny, is because everyone goes, yeah, that's not how it works. And yet, if you have a conversation at a social gathering and you say you're a physics teacher, the immediate response is, I didn't do very well with physics. I didn't understand physics. And I point out to them that that's not true. We all understand it, exactly as Kinga was saying. So, can anyone tell me, there's some good stuff in there. There's some absolutely good physics in there. Or bad. I'll take either. Who want to share?
But he compressed the spring, the weight or mass of the rock prevented the rock from moving back. But when he released the spring, it looked like the rock lost mass, and that force was then able to push back on it.
Sure.
And the recoil of the spring is like the recoil of a slinky, so the second hit to the head would likely have happened.
So, anything else? I mean, it actually gets at Newton's third law, right? The spring, there's a force on the glove, and the glove applies an equal force on the spring, and the spring on the rock, and rock on the spring. It's there, but it's also what we call a discrepant event. It's the exact opposite of what we expect to have happen. That's kind of more of the same. So, I always...
He's going to put rockets on this.
Sorry?
He's going to put rockets on this thing.
At some point, but not this one. This one is a bit more analog. This one is a little using what's available. His budget was a little less for this one. So students think that everything happens because of what they do. They think they walk because their muscles make them move, but their muscles are internal. And internal forces cannot make you move. Only things that are external to you can make you move. I mean, I can do this all I want. I'm not going to go anywhere. That's internal. And so this one gets at that problem, but it also touches really nicely, going back to our previous discussion. Okay, so the first thing I'd like you to discuss is why the fan sail system won't work. Why that will not work.
That's it. No, I just
Why is it different than the family?
All right. I apologize for interrupting your discussion. So I actually have a worksheet that I usually use to introduce this. This is the Wile E. Coyote possibility. And I wander around the classroom. Right-handed. And so I asked them, well, what made the airman? Okay, and they discuss it. What makes the airman? Why did, I know you won't get to experience it, but I imagine you've experienced band before. Especially this summer. Yeah. Blade is applying force, hitting the air molecules. It's making the air move. Well, if the blade is hitting the air is hitting the blade. And that's why this is what the intelligent coyote would use, not the one we've got. Right? Because then there is an external force. But you put the there, it's just flying, right? Just discuss. It's a hard one. This is not a simple one. Why does it not work?
Shooting to the left wants to push the current, but the force of the air on the sail.
Why does it not move? You want to give us an explanation? Why does it not move? Air's still hitting the blade. That's not changed. But we put a sail on it. So, blade on air, air on blade. That's the external one. That's what makes it move. So that's still there. So there must be something that's adding to it in the other direction. Right? If you still got that force, there must be something that's summing to it, or canceling it out, or subtracting away, however you want to look at it. It's really a summing, but there's got to be something in the other direction. Yes?
The air on the shield wants to push.
Exactly. That same air that you hit is now hitting the cell. And so you've got those two forces, but now you could also say that's now internal. Right? If you look at the whole system, there's nothing external to the system. Yes?
Why is it so balanced? It would seem to me there'd be some air getting around the sail, so it wouldn't quite be balanced. I mean,
It's nice to do it on a table that's both level and has a little bit of friction. Yeah. You're absolutely right. But even if it wasn't perfect, it's way better to just not have the sail at all. This group had an additional problem with that, and that was that there was no source of electricity. This video solves that problem. And actually, this is the original. This is the one when all the physics teachers look at. All right, please discuss the multitude of things that are wrong with that one. It's just so many.
I'm gonna say that's the plus 2 for
Would be flowing to get back.
Maybe if you just close his eyes and sit down and recognize the issue mindful, he might actually be across that entire gap. So the fun fact, runners, coyotes aren't fast. So you can actually run faster. Maybe that's the inside joke. Like, the overall what the inside feels like. He actually is faster than should be good.
All right, start us off. There's so many things. Let's skip the sail and fan one because we've already dealt with that. Give me some others. Some fundamentally wrong physics. And even if you don't know the physics, there's some things that are just so fundamentally wrong, you know the physics. And that really gets back to we all do. Yes?
The absence of gravity.
Absolutely.
Except when it was coming.
Yes, except when he had nothing else that he could do. Yeah. Like what should have happened the moment that he left the cliff edge? Yeah, so it started to fall. And then he would have slammed into the other cliff. It wasn't really a better option, but what else? What happened at the moment the thing unplugged? Yeah, exactly. Exactly. And there's many, many, many others. I'm afraid, just like with humor, I only have a few chemistry cartoons. There was only one I found in the entire, so here it is. All right, discuss the chemistry and perhaps the optics. does this demonstrate chemical change?
Is it changing the color?
Absolutely. And as he's mixing the paint. Anything else? What seemed to also cause a color change? Mixing certainly did, absolutely. Impact, absolutely, right? Pressure. Right? There are chemical changes that will happen under certain conditions. Very high pressure.
Would you like to immediately pour these chemicals to a labeled container, which would be a high on the lab safety?
Yeah.
There's no question which colorless liquid was in that lab container.
I think he probably
That's true. Or yeah.
he did some demonstrating with the MSTS bit, but not so much the other. And you can get into actual discussions about invisibility cloaks and metamaterials because we're actually getting there, right? They actually have metamaterials now which it's worked for microwaves. So they send microwaves, it's guided around the object by the metamaterials, and it's as if the object isn't there. So this is actually, it's not science fiction, it's science. And we're going to see this in the not too distant future. Hopefully for better causes than. So quite often you see engineering, right? He designs his traps. So it's a little hard to read. It's a Roadrunner lifts glass, pulling up match lights fused to TNT, boom, ha-ha. I would assume there wouldn't be anything left to eat, but it doesn't always do it rationally. And here's the engineering in action. There's another engineering one. Actually, I like this one. This would be even better if I showed it to you. It's dropping an anvil on the Roadrunner. It's actually some really quite good physics there. So, give you probably one more opportunity to discuss. want to share what was in it that actually made sense. It was Tom. Yes. Sorry? Oh, nice. Right. Different terminal velocities. Very sophisticated. I didn't come up with anything nearly that clever. But you're absolutely right. What else? I mean, the angle, the releasing of the angle is kind of a classic physics problem, right? You've got a spring that's storing all kinds of elastic energy. You've got to balance the upward force of the spring and the downward force of coyote plus anvil is in balance. Drop the anvil, no longer in balance, up goes the coyote. And anvils are pretty heavy, very, very heavy. All right, I only have about another 30 slides left, so we won't be going through them. With my grade 12 college students, the last week is their culminating task, and they build a Rube Goldberg machine. Right? Really, really complex machines that do absolutely nothing of any intrinsic value. And so here's an example. Oh no, that's not the one. It's okay. It was a nice example of simple machines. This one is one I want to show you. And I think that's a good point to end it. And I'm happy to answer any questions and stay around and talk if you want to discuss any of this. I mean, it's just kind of a fun way to get our students engaged. They love it. You can get at some really cool ideas, and anytime they're engaged is good. And we didn't end up using the cards, but you got the idea of what they're for. All right. Thanks. Enjoy the rest of your day.
I'm sorry, I've moved around all the time.